Hi students, I have decided to record a video on the A-Level November 2010 Paper 2 Question 2. Alright, I know this question you may find it difficult to do because there are a lot of information to process. So I'll bring you through the steps, but do not afraid if such a question comes out in your exam or in A-Levels, because all the concepts tested will be things that you have studied before, so you just have to break down the information into things that you know. Okay, so for example, in this question, if you look at the first question stem of this question, it says that 1-bromobutane can be made by reacting butane 1-or sodium bromide and corn sulfuric acid. So one look at the first statement, you should already know what is the reaction that is taking place. Okay, so if you look at 1-bromobutane and butane 1-or, you know that there is a conversion of the functional group from alcohol to alkyl bromide. Alright, so if I break down the steps for you, okay, what is happening is this. Okay, sodium bromide reacting with sulfuric acid, corn sulfuric acid, giving you hydrogen bromide gas, HBr gas, and the other side products. And using the HBr gas, you will then be able to convert this alcohol functional group to an alkyl bromide functional group. And this is actually a familiar reaction to you. Alright, so therefore, if we continue to read on the question, it then gives you this table of information, okay, which you will be able to use it later on. So do not be afraid first. Then if you continue to look at these boards, it tells you the step to prepare impure 1-bromobutane. The reason why it is impure is because after you go through steps 1 to 4, you do not obtain a pure 1-bromobutane. You will obtain 1-bromobutane plus some side products. Therefore, it's an impure 1-bromobutane product. Okay, so I will bring you through steps 1 to 4 first. Okay, so in step 1, the question tells you to place that all these reagents, they are placed in a 2-neck flask, which is this flask over here. Alright, and one of the neck is placed with a tap funnel. Okay, so one of the neck is placed with this tap funnel over here, and then after that another one is placed with a condenser. Okay, so this one you should be quite familiar already from last year promos. And after that, in step 2, it says that corn sulfuric acid is placed in the tap funnel. Alright, so corn sulfuric acid is placed there, and the acid is added drop by drop into the reagent flask, into this 2-neck flask. The contents are well shaken and cooled occasionally in an ice water bath. The reason why an ice water bath is needed, so wherever ice water bath or something cold is needed, or they say that cooling is required, it means that the reaction must be exothermic, and therefore a water bath is needed. Alright, so in step 3, it says that when all the acid has been added, gently boil the mixture for about 45 minutes. So take note, they actually provide you with the time as well. So therefore, in planning questions, when you write down the steps, you must write down the amount of time needed as well. Okay, so upon boiling and shaking the flask gently, you will actually produce the desired product. Okay, the desired product, which is the 1-bromobutane product. Alright, so while heating, like what I've mentioned earlier, this reaction is taking place, and then with the HBr gas that is produced inside your 2-neck flask, okay, inside this flask, butane 1-or that is also inside the flask will then react with your HBr gas to produce your desired product. So this is your desired product. Alright, this is your desired product. Okay, and wherever you look at corn sulfuric acid, you must remember that 2 types of reactions can occur. for organic reaction. Number one, okay, I'm here now. Number one, for organic reaction, when there's corn sulfuric acid, you must think of elimination reaction that can take place, which means if there's an alcohol, dehydration of the alcohol to give you alkene is possible. Number two, condensation reaction could take place if there is both the carboxylic acid and an alcohol present. However, if you look at this reaction, there is an alcohol, yes. However, there is no carboxylic acid, which means that elimination is possible, but condensation is not possible in this case because no carboxylic acid is present. Alright, therefore this one is not possible. So elimination could result in a possible side product. Alright, and if you study your inorganic later on in one of the chapters from group 7 of inorganic chem, you will also learn that HBr, in the presence of corn sulfuric acid, it will produce Br2 gas as well as sulfur dioxide gas. So this other inorganic reaction could produce another 2 side products as well. Okay, so this one you will learn later, so don't worry about it first. But one thing I want you to take note is that because it is corn sulfuric acid, therefore the state symbol that I use over here is liquid. Okay, so wherever it is corn concentrated, then the state symbol used is liquid. Similarly for HCl, if it is concentrated HCl, the state symbol is liquid as well. If it is aqueous or dilute acid, the state symbol will be aqueous. Okay, then next, if we go on to step 4, so at the end of step 3, you will see that you will have inside your 2 net flasks, you have this thing. Okay, over here, you should have the excess sodium bromide. Okay, whether sodium bromide is in excess, or your butane 1-ol is in excess, this one you need to calculate. Okay, this one you need to calculate on your own using the volumes and using the mass given. Alright, and after calculation, you'll realize that sodium bromide is in excess and corn sulfuric acid is also in excess. Okay, and there will still be water inside your 2 net flasks plus your desired product. And of course, in every reaction, there will be unreacted reactants. So in this case, butane 1-ol, although it's not in excess, there will still be some unreacted butane 1-ol present. Alright, so in step 4, it tells you to rearrange the apparatus for distillation. So this setup over here is actually a distillation setup. Okay, so if you compare the setup that I showed you just now for steps 1 and 2 and for step 4, it is different because for steps 1 and 2 is using a condenser only. Alright, that one is a reflux setup. The condenser is used and there's no collection of distillate. However, in step 4, you can see that there is this part over here which is the collection of distillate. Okay, so this is a distillation setup with the thermometer present. Alright, and if you recall from your secondary school knowledge, you should know that for distillation, it works on the basis of boiling point. Therefore, the thermometer is needed. Okay, and hence the question actually gives you the boiling point of the compounds. Okay, so if you compare the boiling points, you'll realize that these 3 boiling points, they are very similar. Alright, and what you want actually is 1 bromobutane. This is your desired organic product that you want to get it as a pure product. However, because when it reaches 100 degrees Celsius, water will, when it reaches 100 degrees Celsius after heating out the reaction mixture, water will actually come out as a distillate first. Okay, and by right, the thermometer, once it shows that it is above 100 degrees Celsius, because at 100 degrees Celsius it will stay until all of the water comes out as a distillate. Then it will continue to rise until no more water, when there is no more water. Okay, and when it reaches 102 degrees Celsius, 1-bromobutane will actually start to come out as a distillate now. However, because the temperature, the boiling point of water and 1-bromobutane is so similar, it is possible that both compounds come out at the same time as the distillate. Okay, and therefore this 1-bromobutane that you obtain over here, okay, in the distillate over here, is actually impure because there could be water present inside this distillate mixture. And also, if you look at the butane 1-ol boiling point, 118 degrees Celsius, is also considered similar to 1-bromobutane boiling point, and therefore it could also some of it could also be present inside your distillate that is collected for 1-bromobutane. Okay, hence after step 4, it is needed to purify your impure 1-bromobutane distillate collected, and therefore you will need steps 5 to 9 to produce a pure 1-bromobutane. Alright, so I'll bring you through steps 5 to 9. So if you look at step 5, okay, usually for purification of organic compounds, after you obtain it from the reaction mixture, we will purify using the separatory funnel. This is very standard. Wherever I do it in the lab, I also use the same steps. Okay, so you will use a separatory funnel, and using a few steps, using the same technique of separation, using the same separation technique using the separatory funnel, you will actually be able to produce or get a pure product, okay, the desired organic product. So for step 5, it tells you to shake the distillate with water in a separating funnel. Okay, separatory funnel and separating funnel is the same thing. And then separate the aqueous layer from the 1-bromobutane and reject the aqueous layer. So now I've drawn two diagrams. The first diagram over here, alright, the first diagram, this one, you can see that this one is not the exactly what happens, but you can see that initially the distillate, which contains 1-bromobutane, butane 1-ol and water, will be found in one layer, and the other one, the water that is added, okay, the water that is added into the separating funnel is found in another layer. Alright, and therefore there are two layers. Okay, the reason why there are two layers is because both layers are immiscible in each other, which means they are not soluble in each other. There is no effective interactions between the two layers, the organic and the aqueous layer. Hence, there are two layers, and the reason why one layer is above the other is because of the differences in density. Okay, so if you look at the density of water and the density of the other two compounds, water is 1.00, 1-bromobutane is 1.35, which is much higher than water, and therefore your 1-bromobutane will be in the lower layer, okay, and water or the aqueous layer will be the top layer. Alright, okay, so upon shaking, some of the butane 1-ol will move to the aqueous layer due to the hydrogen bonding with water. Alright, so this shaking process, it doesn't make all of the butane 1-ol to go to the aqueous layer. That is the reason because, there's a reason for this, and that is because some of the butane 1-ol left in the organic layer, over here, I've written down, left in the organic layer, there are still effective interactions between the butane 1-ol molecules with its own butane 1-ol molecules, as well as the butane 1-ol molecules with the 1-bromobutane molecules in the organic layer. Okay, and therefore it requires a few rounds of shaking for it to move to the aqueous layer to hydrogen bond with the water molecule. Okay, only when there is effective interaction between the two molecules, then it will stay in that layer. So in this case, because the butane 1-ol molecule can have interactions with both the 1-bromobutane and can have interactions with the water molecule, therefore it will be in both layers. It can be present in both layers, and it depends on how much you shake. Okay, so after this step, inside this flask, after you release the bottom layer, okay, and close back the tab of your separatory funnel, okay, so this is the tab. So once you see that, okay, the line of the upper layer is reaching, then you close the tab. Then whatever you have collected over here, okay, whatever you have collected over here is actually 1-bromobutane, as well as some of the leftover butane 1-ol that has still that are still with has interactions with the 1-bromobutane molecules. Okay, whereas for the aqueous layer, okay, for the aqueous layer, the water and some butane 1-ol is present, and this layer is actually discarded because we don't want this layer. What we want is the 1-bromobutane compound. Okay, and therefore you will go through step 6 and step 7. Okay, so step 6, you will add, same thing, whatever you have collected in the conical flask, you will now pour into this separating funnel. It's the same separating funnel, but the aqueous layer from the previous time has already been thrown away. Okay, so now this separating funnel, you pour back the conical flask compound, which is 1-bromobutane and some butane 1-ol, and then you add in aqueous you add in con HCl, which is the aqueous layer now. Okay, so the step 6 is here. Okay, then upon shaking, this is what happens. Upon shaking, this is what happens. The alcohol will actually attack the H plus of the HCl, alright, will attack the hydrogen of the HCl, and it forms this protonated ionic compound over here. It forms this ionic compound. This is actually a very uncommon case. Usually alcohols will not attack the acid. However, in this case, because concentrated HCl is used, so number one, HCl is a very strong acid, okay, so it dissociates to give you H plus and Cl minus in water. Number two, because it's very concentrated, and therefore the concentration of H plus is very high, and hence the oxygen of your alcohol, when there's a lot of H plus present in the reaction mixture, it's possible for it to be protonated to form the ionic compound over here. Okay, it's actually OH2 plus then Cl minus. Okay, but if you write plus, Cl minus is also correct. Okay, and therefore, because of the formation of this ionic compound, this can form ion dipole interaction with a water molecule, and hence it will be in the aqueous layer instead. Therefore, when you look at the resulting separating funnel over here, after you release the organic layer, you should be able to get only the 1-bromobutane. All of the butane 1-ol should already be in the aqueous layer now by this step 6. However, in the 1-bromobutane, there is the possibility of having some concentrated HCl present in the conical flask. Okay, you may not know because the excess con HCl, some of it, when you are releasing into the conical flask over here, some of it may be released into a conical flask as well. Okay, so to keep it safe, so that such that there's no con HCl inside your desired organic product, we will go through step 7. Okay, so in step 7, you will pour in your conical flask from step 6, okay, step 6 conical flask into this separating funnel. Then after that, you will pour in sodium carbonate as well, and this reaction will take place. So sodium carbonate will react with your HCl to give you sodium chloride, carbon dioxide gas, and water. And sodium chloride and water will definitely be in the aqueous layer. Alright? And whereas for your 1-bromobutane, it will remain in the organic layer. Okay? And then after that, after you go through, you open the tab and get the organic layer, you should be able to get the desired 1-bromobutane as the product only. Okay? However, there's a possibility of some water being present in the conical flask as well. You may not know. We may not know. Alright? And okay, I just want to take this opportunity to alert you. Okay, the reason why step 7 it says release the pressure at intervals is because of the production of this CO2 gas. Okay, because when this neutralization reaction takes place, carbon dioxide gas is actually produced. And when you're shaking, you actually stopper your separating funnel to shake. So at intervals, you must take out the stopper to release the pressure of the CO2 gas, because or else there will be a build-up of pressure due to the CO2 gas that is being produced when the reaction is taking place. Okay, and then for step 8 now, okay, the only thing that I want to highlight is that they use anhydrous calcium chloride. So wherever question tells you anhydrous blah 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 is used, whether or not it's an organic question, when they say anhydrous something is used, always take note. Anhydrous means it's dry, so most likely it's used as a drying agent. Okay, and a drying agent is used to remove water. Alright, so wherever question gives you anhydrous, you know that there must be some form of drying or dry condition is needed. Alright, so then after that, step 9, they ask you to filter the 1-bromobutene into a round bottom flask and distill it again, okay, in order to get a pure compound. Alright, so the filtrate will be your 1-bromobutene, then after that you use distillation again to get your pure 1-bromobutene. So this is actually the steps that you need to take in order to produce a pure organic compound. But on paper, we always write it as one balanced equation only. Alright, however, actually there are so many steps when you really do it in the laboratory. Okay, so because Cambridge actually provides provides all these steps as one of the question in the 2010 paper, they will actually expect you to know how to write the steps if they give it to you as a planning question. So please make sure that you understand each of these steps so that if it comes out as a planning question, you are able to write it out in this form as well. Alright, so that's all. If you have any question, you can come and ask me.